All right, welcome back for the second part of the video. Again, this is chapter 17, second lecture. So the second half of chapter 17, and this is the second video of that second part. Still with me here? All right. The first part talked about streams and different types of streams and erosion and deposition. And then we got into stream channels of degradation and aggradation. Now we're looking at how a stream grades itself over time. Well, for a graded stream, it first starts with an uplift. Right, there's some geomorphological process lifts the landscape up. It then rains on that landscape and water is moved down slope, because if the ground lifts up, the higher it lifts, the greater the slope. The greater the slope, the faster water runs off. The faster water runs off, the more material it can possibly carry with it. So uplifts don't occur in a perfect slope. So the undulations in the uplift are slowly smoothed out over time through a process of excuse me, erosion and deposition, the degradation and aggradation. So if we take a look at its base level, that's the lowest level in which a stream can grade itself downward into. This would be your major body of water, like an ocean. One time the Mississippi River, in the whole Midwest United States kind of looked like this. And over time, lakes have formed, the flat, homogeneous areas have pooled to form the lakes. And then stream channels are created from one storage area of water to another one, eventually down farther and farther until it reaches the ocean. And over time, it's been moving the material from up high and depositing it down low. Now, again, I mentioned it starts with an uplift. And say, for example, you have a fault, a break. We'll get to this later when we talk about the lithosphere and tectonic plate movement. But there's oftentimes in our planet's history, we've had material move up and move down and away from each other, a fault. And water starts to move over that uplift. Water starts to erode away that area, and that's called a nick point. We just know them as waterfalls, but the proper term for water moving from a high uplift to a lower landscape is called a nick point. Probably the most famous nick point waterfall in the United States is. Has anybody been to Niagara Falls? Check it out. I hope this link works. Yeah, there's half of it, the horseshoe bend there, and it's United States on one side and Canada on the other side. I don't know which is which because I've never been there and I didn't study it. But as you can see, the landscape in the background is much higher elevation than the landscape down below at the river. And then as the river continues on, then it creates a nick point waterfall. And this water, because it has energy and it's also changing directions, exerts a force on the edge of this bluff, or this uprise, lifted area, and so it erodes away that edge over time. Over time, the river degrades the river channel by removing material out from it, and therefore it incisors itself down into the landscape. And that means it gets closer and closer to the river valley below. And so the waterfall gets less and less. Basically, the nick point is smoothed out over time. If you look at Niagara Falls without any water in it, crazy, huh? You can see that all of this rubble down here used to once be way up there, and the water has broken it apart and deposited it technically downstream. Now, as the water continues to crash onto that rubble, it breaks it apart even further into smaller and smaller pieces until finally it can become bed load. And then the bed load is dissolved even more into suspended load. And then this suspended load can dissolve even more into dissolved load. That's the Niagara Falls. The interesting thing is this actually happens at a pretty fast rate. Obviously, you could stare at it all day and you'd never see the river move back. But if you went to visit Niagara Falls every 5 or 10 years, say you get married at the Niagara Falls, and for your 5 or 10-year anniversary, you go back there. Every time you go back there, the landscape would look different at the falls. If we just take a look at recorded history of when we started actually marking where Niagara Falls was, it's moved back every 50 to 60, about 50 or 60 years worth. It's moved back a pretty large chunk from being right where it was when European explorers started recording it. You can see it'll eventually get back and touch this island, so the channel will split, and you'll actually probably see them turn this into some sort of a viewing station, because you'll have the falls to your right and to your left. Also here, there's a little island there that'll also possibly turn into a new outlook station. So that's 1886 there, and this is probably 1990 something back here. In our lifetime, it may move all the way back to this island. It's moving at a pretty fast clip there. Every 70 or 80 years, it moves back about that far. Before you kick the bucket, you might want to check to see how far back it's moved. After a while, oops, that moves it. After a while, the river channel incisors itself all the way down to the lower floodplain, to which then it starts eroding outward instead of downward, because the water moves a lot slower, because it's not being plummeted down that such a large drop and picking up all that energy from gravity, and the floodplain widens out throughout the lower and upper parts of the river channel. Now let's talk a little bit about stream meandering. Streams meander, they weave back and forth across a homogeneous landscape. And how does it do that, or why does it do that? Well, physics. And I'm not going to get into it in super detail because this isn't physics, but we need to have a little basic understanding of it, because it's the land shaping and morphing process of the environment. The hydrosphere changing the lithosphere, and the lithosphere also directing in which way that works. So not all dirt is created equal. Not all of the land is the same density as other parts of the land. Some parts of the landscape have trees with big roots. Some have no roots holding the dirt in. So some parts of the lithosphere is more susceptible to other parts of the lithosphere in erosion. Erosional processes can impact them greater than others. Take, for example, a forested area. Those roots are going to want to hold on to that dirt and not allow the river channel to wash it away, per se the other side, which might only have shrubberies or grasses, which will be easier for the water channel. It's moving straight through an environment to eat away at one side of it faster than the other. Okay? And so that causes the river to start to bend a little bit as it goes around the more difficult places to erode and cuts into the easier places to erode. And that sets off a motion. I'll ignore this animation. I thought I deleted that, but I guess not. It sets off a chain of events that causes this movement around and through the environment to exacerbate itself and get larger and more dramatic as time goes on. And this is because of the water molecules and the physics of water. If you'll recall, when we talked about atmospheric lack of bonds of H2O molecules in vapor, and in its liquid state, it's kind of loosely bonded. And then in the frozen state, water is in this crystalline structure. Well, that loose water bond is sort of like holding your bestie's hand. You guys can step away from each other a little bit. You can dance and twirl around. One can jump up, the other can dip down. You've got a little bit of flexibility and leeway, yet you're still kind of, holding hands and bonded together. Well, you ever been like holding hands with somebody and you're like walking through the mall or something, and you have to take a left turn to get to Panda Express, and then the person on the inside takes a sharp turn, and the person on the outside kind of lags behind, but you're still holding hands, and so you kind of swing them around to catch up with you, right? So you can still walk together and talk together. Well, that bond, that force is exerted on the other molecules that are on the outside of a curve that starts to form. And that force that's transferred to those water molecules give it more energy, and so it can eat away at the outside of the river channel and pick up more load, rocks, dirt, debris, and carry it away. So as the stream starts to go around more difficult areas to erode, it starts eroding more on the outside of the stream. And then the inside, as you recall, you have to make that sharp turn. You actually slow down, right? You take a couple tiny steps around the corner, and your friend takes big steps to catch up to you. Well, that slowing down around the corner on the inside bend means there's a lack of energy or less energy of the water, so the load starts to drop out. So on the inside curve, what happens is these point bars are created from material that drops out of the river, while new material is being picked up on the cut bank. And then as it meanders the other way, the stuff that was picked up at the cut bank forms the next point bar. Say it's like drop off a load, pick up some load, drop off a load, pick up some load. And so these meanders start working themselves through the environment. Here's a sketch example, but if you recall a couple slides ago, and actually one whole video part ago, you had that aerial view of a meandering stream, and you could see where there were marks in the landscape where the water, when I said the water used to flow. Those are called oxbow lakes, and when they dry up, they're called meandering scars. Okay? So if you have a river that's meandered, and say there's a flood event or some sort of force, and this neck becomes susceptible to that force, it can blow through. Water's lazy, the environment's lazy. It always seeks the most easiest direct path down slope. And so the water is going to want to go straight instead of meander all the way around that oxbow lake. And it does. It starts going this way and this way and this way. And then as the channel deepens, it can deposit material here and cut off that meandering curve and turn it into an oxbow lake. So in any given floodplain, in a meandering river, you can see the meander scars, maybe even some oxbow lakes that are not quite completely dry yet, because the channel is so deep, it'll hold rainwater for a much longer time. Because it's interesting, this is an actual riverbed, which is different than the soil in the floodplain. So it holds water, and when it dries out into a meander scar, it's a completely different ecosystem than the floodplain around it. Crazy, but cool. You also notice that there's a couple other terms I want you to know about that occur in a river floodplain, like natural levees. This is when a flood is reduced and dissipates. It leaves two things. It leaves back swamp, which is your light, nutrient-rich material in the floodplain that spurs growth, and that's why we farm in the floodplain, because all this back swamp is the rich nutrients that were dissolved in suspended loads, like the biomass that gets deposited there, while the heavier rocks and rubble get deposited on the cut banks, which slows down the natural rate of erosion, and the meandering just doesn't go crazy. If it wasn't for these natural levees being deposited after a flood event, stream meandering would be a lot more dramatic than it is currently. So there's one other type of river I'd like to mention, and this is an entrenched meander, okay? Up till now, we've talked about how, like, the landscape is modified, like there's a change in the lithosphere, and then the hydrosphere starts working on it, right? Precipitation, percolation, groundwater movement, erosion, and deposition. Well, there is you could reverse that. You could flip-flop that, pull an Uno on it, okay? Reverse. What if the river existed as a meandering stream and that landscape was lifted up? Now it's more susceptible to gravity because it's higher up than the ocean floor where it wants to be happy and stable. So what happens is gravity pushes down on it and it entrenches and it does more degradation in the channel than aggradation. So instead of continuing to widen and create point bars and cut banks, it just incisors or entrenches itself downward. Does anybody know? Well, it says it right there. Okay, this is the Colorado River forming the Grand Canyon. Okay, the river was there first, then the Rocky Mountain uplifts occurred, and so it's been eating its way down through literally billions of years worth of sedimentary deposit here, because this used to be all an ocean floor a long, long time ago. So we're looking at floodplains, valleys and floodplains. There's these things called alluvial terraces. When a flood event occurs, the stream channel is obliterated. And when it settles back down, it settles at a lower channel than it started with. And that whole blown out area creates a slightly narrower floodplain, and it creates a terrace effect to the sides of the river and reduces the actual floodplain. Okay, that's called alluvial terraces. It downcuts in its own stuff that it's carrying. You know, the aggradation in the channel is lower than what it used to be, and so the stream has cut itself because of a flood event washing everything away, a slightly less wide floodplain with a deeper channel that also begins to meander again. So we look at a graded stream model. Okay, we're bouncing from stream to stream here because we're talking about all sorts of different topics to do with one stream versus another stream, mentioning all the streams and talking about how they work. Well, the graded stream model has three distinct parts to the graded stream. There's the upper, middle, and lower reaches. And one really good example of a graded stream model, of course, is the Mississippi, but also the Rhine River in, well, Austria, Germany, the Netherlands, and France, multiple countries here. Maybe Switzerland? Yeah, Switzerland, sorry. So a graded stream model works itself over time to achieve a perfect slope to move water that occurs in and on the landscape from precipitation events out and down back into major bodies of water. The upper reaches, or the beginnings of this graded stream, is a mountainous area or a high elevation area, which means it's more susceptible to gravity, which means water moves faster and incisors the channels deeper. So the stream channels are very narrow V-shaped and the density is lower. There's not as many stream channels. As that stream makes its way down the slope, it gets closer and closer to, the level of the ocean. And so it begins to slow down because it's not as susceptible to gravitational forces because it's getting closer to being stagnant in an ocean, or it's not being pulled down anymore. Right? The higher you up, the farther you fall, sort of thing. And so here you start to get some material dropping out, river channels widening, because now it can, as it slows down, it starts eroding from the banks equally as it's digging itself down in the channel. And you start to see more tributaries connecting, streams widening, carrying more sediment. And as it slows down, because at a confluence you have two vector forces intersecting with each other and then going in a totally opposite direction. So that just like Hot Wheels slamming into each other at an angle, they slow down a little bit. So the water in those channels where it has a confluence slows down, material drops out, lessening the slope even more over time. Finally, when the water makes it down slope even farther to near sea level, the floodplain starts to widen out even more. And the river channel plains widen out because the water is slowing down. The material, the heavier material is dropping out into the bed, which makes it more difficult to erode, and so it erodes away from the banks a little bit easier. And you start to get a very low slope, low water velocity, and a creation of a wide valley and floodplain. Now that we're done talking about erosional processes, I literally spent 90% of the time, maybe 80, talking about erosional processes, rivers eroding, degrading the environment. And now let's get to deposition and aggradation. Okay, there's not much to it. Basically, we're just talking alluvial fans and deltas. Okay? As the water slows down, it loses velocity, loses energy. So large parts of the bed load and suspended load get dropped out first, and then smaller particles and smaller particles. And as the energy decreases, so does the ability to carry particles. And so they drop out one size by the other size, smaller and smaller and lighter until there's no more load to drop out. This creates a fan-shaped distribution as the water is allowed to spread outward instead of being channelized because its speed is reduced, right? And that the slope is lessened to almost nothing near where it meets a major body of water. Alluvial fans in arid climates, so when the water dries, there's a depositional event, and then the water dries, and another depositional event, and the water dries, is called a bahada. I don't think I test on that, but it's a pretty cool term to know about a certain type of alluvial fan in arid, aka dry areas. If you go out to Burning Man or something, you may drive across one of these and you'll be able to recognize it. Yep. So deltas are probably the most well-known depositional landforms. When stream channels meet major bodies of water, the sediment drops out in the process. It's called sorting, that I talked about just a little bit ago. And the distributaries are all developed within the delta that carries the water out in a very broad pattern. If it becomes large enough, that it can be called a bird foot delta. Example would be New Orleans and the Mississippi area, the Mississippi River Delta. Now, over time, the Mississippi River has changed course and deposited its bedload in different parts of the Gulf of Mexico. Right now, we're used to seeing the Mississippi River go right through New Orleans and out into the Gulf. Here's a Google map of it. You can see that all this land is pretty new as of a couple hundred years. But before that, if you look up north, you can see the very remnants of an old delta that used to be deposited here. And you can even see old stream channels that we still farm the heck out of. Right? The old Mississippi River channel used to come down here. And one time it went here, the other time it went there, and this used to be the Mississippi River Delta. And over time, the waves action of the Gulf has eroded it back to be a smoother curve. Yeah. So, right, that's like basically, about 1,000 years ago, anywhere from 800 to 1,000 years ago, it used to be deposited down here. And then before that, about 2,000 to 4,000 years, about 2,000 years worth of deposit all up in here. And even before that, it used to be deposited way down here to the southwest. So the Mississippi River, just jumping its course a few degrees, causes the delta to grow in a completely different, direction. It's pretty interesting. Like I said, it's going to keep going as long as the river doesn't change course, which we hope it doesn't. But if it does, it'll continue to grow out farther and farther, fill up, and who knows what direction the river will take it. But eventually, maybe it'll connect to Florida, or maybe we'll make a land bridge all the way to Havana. Who knows? There's still a lot of dirt here to erode and degrade and get deposited down out here. I mean, if it made this much land in 5,000 years, and if it were to keep the same channel, another 5, 10, 15, 20, and maybe in 100,000 years, if we're still here, there'll be a huge land bridge. Maybe, maybe not. So now let's end this chapter with human environmental interaction. I want to talk about two things: urbanization and modification of stream channels. Okay, urbanization is really, really bad for stream health and natural ecosystems around streams, channels, and floodplains. Why? Because of rates of influx of water. And this is like the best example of a correlation to us dealing with COVID or some other pandemic like polio or something, okay? It's not about people getting infected or not getting infected and the spread of it. It's the impact it has on our hospital system. People can make excuses all they want about, well, want to wear a mask, not wear a mask, get sick, not get sick, whatever. But if people get sick, they go to the hospital more often than not because they need to seek medical treatment. Our healthcare system in the United States is built upon an analysis of an expected amount of people that get sick at any given time. They come up and analyze this. Okay, we think this many people are going to get colds, flu, sinus infection, cancer, broken bone, everything in the book that you go to a hospital for. They expect, okay, we have 1.3 broken bones a day, 4.8 colds a week. You know, it's all number crunch statistics. And they say, okay, well, if we're going to build a hospital, we know how many people per day we expect to treat, how long they're going to stay here, and when we can discharge them. So we're going to build our hospitals with that many ICU units and this many regular units and this many urgent cares and this many outpatients and this many physical therapists so that they can handle the normal amount of people coming into hospitals. Now, when something like COVID hits and a pandemic hits and way more people experience a sickness that they have to go to a hospital for, it overwhelms the hospital and people die because there's no more room in the hospital. That's the problem. You know, it's not about whether you actually die or not from COVID. It's about the impact it has on our hospital system. And urbanization does the same thing to our rivers, right? Our rivers, the Mississippi River has been minding its own business, taking in its water, putting out its water for hundreds of thousands of years. And it's happy. Yeah, every once in a while it gets overrun and sometimes it dumps more water out, but pretty much it's been in balance and it's trying to achieve that graded nirvana. Well, then we come along and settle all at the banks of the river and then pave over huge swaths of land. And what that concrete does and asphalt does is cause the water that lands on it to immediately run off and go right into the river. And the river isn't built to handle that rapid influx of water. It expected all those water droplets to percolate down through the soil water belt and slowly get released into the river channel over a greater amount of time. That's the green line in this graphic. But because we have caused the water to run off faster and get to the river channel sooner, this is the new input curve to the river. And you can see that it's the same amount of water from point A to point B, time A to time B, but it just all gets there sooner at the same time and causes flooding to occur. And the river's like, it's not my fault. That stuff was supposed to percolate. So we as humans and paving over the landscape around rivers are causing worse flood situations because of our inherent need to pave over things so we can get to our work, so we can make tons of money to enjoy Starbucks, right? So think about that. I mean, have you ever seen like a big parking lot and then there's a big hole in the ground next to it? That's a retention pond. Like by law now, big parking lots have to collect their runoff water, and then that slowly is allowed to dissipate into the stream network. So that's kind of our response, is to dig a big ditch and let mosquitoes breed, you know, West Nile virus and then kill us that way. It's just as much as we try to engineer around nature, we're just shooting ourselves in the foot every which way you go, right? So what we have to do is we have to build artificial levees and artificially raise the riverbank to accommodate our urban sprawl. And that has negative effects on the ecosystem that expected the flooding to occur all around the river that's no longer flooding, right? Animals have to move somewhere else, and then the ecosystem collapses. Then all you're left with is basically a glorified ditch. It's no longer really a river, a ravine, and an ecosystem around the river. It's just a channel of water. It's hardly even natural anymore, which means it's no longer a stream. Yeah, so think about that. Second, dams and reservoirs. Now, you can't completely get mad at dams, right? That was like the best way to generate electricity in remote regions for a really long time, right? Block up a river, you have a fresh water supply, so you can not worry about drought and running out of water and people dying. But you can also then let the water fall over the edge and, you know, spin a wheel and, you know, grind your corn or generate electricity. It's a brilliant design to do. However, it completely destroys the ecosystem above and downstream, and that has devastating effects to the landscape around the river and the stream. So while it did benefit humanity, now that we have wind power and water power, nuclear power, and all these other different powers like tar sands and stuff that are easier to get, we really don't need to dam up our rivers anymore. Yeah, it's good for fresh water supply, but there have been so many studies that have shown that if you return the river back to its natural state, not dammed up, the entire ecosystem will recover to its pre-dammed up days. And not only does the ecosystem and the earth and the landscape become happier, we then can become happier because there's more biodiversity, more, you know, it's how the planet's supposed to work. It's not some dystopian future where everything's concrete and steel. There's actually wildlife. Fish continue to spawn. Salmon are able to repopulate and reproduce. And all these other fishes that existed that couldn't climb a dam or get over a dam now are allowed to go back up. And that brings birds back in, that brings other larger animals, and the whole cycle, you know, regenerates itself. There's a really good video. Actually, it's a film, and it's about 15 or 20 minutes long. So I encourage you all to watch this video about the positive effects of removing dams in this one area, the Hudson River. I know some people complain that their pretty view of the lake will be destroyed if all that lake drains out, but you know, what's more important, the ecosystem in our planet or somebody's property value and their, you know, non-right to have a view where they buy their house? I don't know. You tell me. You know, keep destroying the environment or build pretty sceneries. It's a pretty pretty caring thing to do, if you ask me, but it is what it is. Some people like to look at pretty things, but there are great expanses of nature out there that are beautiful to look at. You don't have to create a dam for that. So there's been a move and a push to destroy a lot of the dams that are inoperable and aren't used anymore. And that is a process that's going on, but it does take money and time and energy and effort. And so the local community has to be behind it, or it doesn't happen. That's all I have for today. Thanks for showing up and listening to the lectures. Again, this is chapter 17, part 2, video 2 of 2. And so this pretty much ends the lecture part of class today. If you have a proctor who's giving this class, if they're a geography professor, they'll be able to answer any questions you might have or have developed throughout this lecture. Feel free to ask them. If not, please shoot me an email and I'll get back to you about this topic. Okay, cool. You'll have a good one. I will go over lab exercises and discussions in a future video or class, but it is a reminder, the lab instructions are already on YouTube. You can hit those up there, and the discussions are pretty straightforward. All right, see y'all.